I'd like to introduce Matt Ziegler, who's Director of HPC for Lenovo, who's going to talk to us about harvesting tomorrow's technology for today's problems. So, Matt?
Great, thanks. Can you guys hear me okay? Sorry about that. So I like to walk around, so hopefully it keeps it, you don't have to try to follow me because you'll hopefully be looking at the slides. I guess this is the part of the show where one of the sponsor gets up and just gives a sponsor talk. I don't want to make it into a, here's our products, here's our product line, anything like that. What I wanted to talk about today was actually challenges that I have on a day-to-day basis, which is what technologies should we actually adopt to put into our product line. This job that I was in used to be extremely easy. Now it is extremely difficult because there's so many different technologies out there, from CPUs to networking to storage. Storage is just getting absolutely insane with where it goes and how we use it in computational environments. And so I'm going to spend most of my time today just talking about that and some of the paradigm shifts that's coming. So in HPC, there's 4 kind of points that I want to make. On our team, we actually have a mission statement, which never happened before. I did come from IBM when Lenovo bought the System X business and brought it over to Lenovo. So we have a mission statement. But these 4 points, Lenovo in 2 years went from 0 systems on the top 500 to 92. And on Sunday, I've got to do all the new submissions for the November list of the top 500. So hopefully we'll be over 100, which is representing 20% or more of the total systems in the top 500. That just is the amount of focus that we're putting into high performance computing here at Lenovo. On the top right here, when we do design for large systems, when there's a system like here at Birmingham or one that we're installing down in Italy right now, or these large, long design sales cycle kind of things, they were all very homogeneous. So from about, and I'll show you some data, from about 2002 till about 2 years ago, it was extremely easy to answer an RFP because you would say, just give me x86 and the fastest network. And you would design these where the systems, it doesn't matter if it's the first node or the last node, they all look the same. So within a system, it was very homogeneous. That is now kind of changing. Most of the systems, I had our senior vice president in the last June top 500 list ask me, where are all the universities? And I said, well, the universities are actually in this whole paradigm shift where they're not building general purpose machines anymore. They're building fit for purpose. They're building heterogeneous systems. They're doing machine learning that requires offloads. They're bringing in FPGAs and GPUs. And they're not having the same Intel Xeon stack in there. So when you look at a system in a university, it's very heterogeneous now. So the top 500 requirement says you should run a LINPACK benchmark across the whole system to get a number. It's very difficult to do that on a heterogeneous system and be quote unquote fast as what the top 500 system will be. So you're seeing these larger systems now become very heterogeneous as exascale kind of pushes new technology. You know, I'm never going to get the exascale with an x86 unless I've got an entire country size worth of data center and multiple megawatts of power to be able to do it. So we have to think of new technologies to get there. On the bottom left, accelerators, especially for machine learning and deep learning. And this is probably the biggest challenge that we have as a technology company is we're being told, you've got to do it this way. And so you see some technologies companies that just say, okay, I'm going to build a box with lots of GPUs. And you have other ones like us who are trying to take a step back and look at the ecosystem and say, how is it being used? What is the software being used? What are the models that you're ingesting into the system to try to come up with a smarter way of actually introducing technology into the ecosystem. And that brings me to the 4th point here, which is, from our point of view, making a server is very expensive. So I know a lot of you that use HPC think of it's just commodity. It's commodity, low cost, low price. How do I do this? But at the end of the day, it can cost 10 to 20 to $30 million per system when you look at how it gets tooled up, the investments that you have to make, all the development costs, et cetera. So we want to make smart decisions. We want to make sure that our research dollars on our side actually make sense. And with the landscape being so different, it's quite challenging for us. So I did want to bring some attention on it. Now, I actually do this for my sales teams because every time that we change technologies, they freak out. And they're like, I just learned how to sell this. Now you're going to change it all. So this is a chart I made for them. But it kind of gives a good indication of actually where high-performance computing has actually gone. And if you look down in 2000, I actually worked on this project with Netfinity servers at Los Lobos and University of New Mexico. This was a cluster we put in. This was actually the birthplace of XCAT. XCAT, open source systems management toolkit, came out of that project where we were just putting Netfinity servers together. And then you move up to 2008, we went from just off-the-shelf systems into hybrid technology. This is a blade center technology that used a cell coprocessor to offload and do acceleration. And just for trivia, this was the first petaflop system, but this petaflop was not achieved with the cell accelerators. It was all x86 cores. So our first benchmark to break the petaflop barrier was still x86, even though if you go look at the literature, they talk about the hybrid technology of cell. We actually did these benchmarks. The size of this system was, we had 15 cluster units, with each cluster unit having 26 racks. So the first petaflop system was about 436 racks with networking and storage total. And when you'll see some of the technologies coming now, we're getting to the point where a petaflop with accelerators can be in a rack, some of the technologies. And then I'm sure when I'm very old and I'm sitting around and I've got great grandchildren, I hope I live that long, I'll tell them how a petaflop is in my watch now or something. Then we moved, and so this transition was more of a technology transition. And then from 2008 to 2009, we actually went in, and the technology was the same, but we wanted to look at the environmentals. How can we actually use lower power and high efficiency cooling into systems? And so you saw a new form factor change, and then into the next scale system that is here at Birmingham. And we're actually looking to change that again. And I'm sorry for the Lenovo salespeople. We're going to change it on you again. It's just what we do. So if you look at innovation was in IT was driven by life sciences. And before this, you saw a lot of like DARPA or military that were really pushing IT, the frontiers of IT. Then it was life sciences. And so as I was at IBM, we actually developed the blue jean system, and it was hilarious when I first started. People thought blue jeans meant what you wore, not that it was life sciences. But it actually was a architecture that looked at, say, how can we basically accelerate the way you do protein folding so that we can analyze mutations within genomes and do drug discovery at the end of the day. So the architecture of blue jean was completely different. And I think we're actually getting from an x86 point of view where you can get to a blue jean architecture. And I'll show you that in a little bit. So life sciences was really pushing the forefront of computing. And now it's actually AI or machine learning or deep learning. You also hear cognitive computing if you're at IBM. There's all these different terms. But at the end of the day, this is now taking and challenging us as a vendor to push the frontiers of computing. And you see this with social media. The most fascinating thing to me is now life sciences was the innovators in technology. Now it's ads on the web. How can I target your shopping behavior or deliver the ad? And that's actually pushing the forefront of technology. And it's very sad that our advertising behavior is actually what's driving the forefront. I was at NVIDIA a couple weeks ago. They're very into the basically driverless cars. That's where they're going to the next gen stuff. Fascinating to actually see it in practice, to be honest with you. So then we take a step back and say, is there really a technology shift? And if you look back at this is the top 500 systems. And if you look back between 02 and 03, you saw this enormous spike, which is basically x86. So I challenge you and say, well, what drove that spike? Why? Look to the left. There's proprietary systems, IBM, Spark, that was HPC, right? So what drove this? How did this dramatic shift in the systems in the top 500 happen? Well, I can give you answers because I guess you're not going to interact with me, which is things like the proprietary systems were very expensive. The operating systems alone could cost a lot more than just buying the hardware. And then you saw basically in that couple charts where I said in 2000 we were doing Netfinity systems, you started realizing there was this price performance. But at the end of the day, you go from 2003 to about 2012, 13, everybody bought x86 systems. That's just what you bought. But was it always good for your workload? Was it the right choice? And when you ask people, they go, I don't know, I just provide the compute. Some workloads work great, some are horrific. Now, then you look back here in 2010, you start to see this accelerator kind of jump on there. And this is to drive the exascale. How can we basically start offloading single instructions, multiple data set type workloads and things that are very vectorized onto these GPUs versus running it on the x86 core? And now you've got Mellanox, you'll say, well, we can offload. How can I basically start taking tasks away from the CPU and make the system a lot more efficient? And this is actually where we're going. And so x86, you start looking at the system design, you'll buy an x86 system, but we're being asked for, how can we use FPGAs better? And if you looked in the news, Intel bought an FPGA company. Why did they do that? Because of machine learning, because of AI, because they know that they're not going to get there with x86 and they have to look at new technologies. So, which one is the best? I have all these new technologies, which one should I choose? Right? So from a company point of view, I have a great partnership with Intel. And when I go meet with Intel, guess how that meeting goes when we talk about NVIDIA? We don't talk about it. And I go to NVIDIA, and they're a good partner with us too, and guess what they don't want to talk about? So every one of these companies, even power is up here, open power. Is that something that we do? And, that's a question we have to ask ourselves as a company. Every one of these companies will tell me, we're the best technology, you've got to have it. Every one of these technologies now costs $20, $25 million to build a system. So do I just throw it out there and see who wins, or do I partner with people like Birmingham or basically the ecosystem that's out there doing HPC and getting feedback from you guys? And not only that, but when I pick a technology, it'll take me 18 to 24 months to basically bring it to market. So it's a time to market thing, which means the days of just developing x86 servers are pretty much over. That's how it always has been. Now I've got to look at different technology choices and say, what is my strategy? Now look at all of these. Go down the list. That is an Intel 2-socket E5, an Intel SMP, or what were the E7s, the 4-socket or greater type of SMP systems. Intel 1-sockets. How many of you guys thought 1 socket would never make a emergence again? It's actually becoming relevant, and I'll show you in a little bit why. SoCs. If you look at the Knights Landing architecture, they now have a -F, a fabric SKU. So you're seeing more, and ARM is doing this, more SoC type systems. Atom, FPGAs, Xeon Phis, NVIDIA with NVLink. NVLink, the link between GPUs so that you don't have latency that's on the PCI network anymore. You can actually basically share models between the GPU rather than having to access host memory. Right? NVIDIA's telling me this is the best thing since sliced bread. It's the best thing in the industry. Now we go do benchmarks and we're like, where's the benefit or where is it not? And that's what we're trying to ask smart questions about it. All the way down to ARM 64-bit. AMD 1-socket is really interesting with their huge amount of PCI that they're going to have in a single socket. Is this a paradigm? But if I showed you this chart 5 years ago, it would have said Intel 2-socket E5, and that's it. That was my job. It was the easiest job, and then I get to live in Colorado and ski most of the time, and now I can't do that anymore because I've got way too many technologies to deal with. Then you look at your HPC workload and you say, what's my characteristic of my workload? Is it memory bound? Is it storage bound? Is it CPU bound? Is it all the above? And now you start taking a step back and you said, well, we give you x86 systems, but your workloads will act differently depending on the kind of characteristics that you have. So now the question becomes, can I develop a system? Can I develop a box? Can I develop a server and a cluster that if you have a workload that is CPU bound, we can run great on? Also, if it's data intensive, could you run great? If it's memory intensive, and this is where you start getting into the paradigm of modularity and flexibility. It sounds great, but it's not easy to do. If it was, I wouldn't be employed, I guess. Now the second part of it is, not only is my workload have a certain characteristic, what about the new technology that's emerging in the marketplace? Every single area of a computer is now emerging with new technology. The storage side, storage is just a nightmare to keep a track of. You now have storage in the memory channel coming from 3D XPoint. From a bioinformatics point of view, I think this could be a game changer. When you look at getting multiple terabytes of flash-based storage in a memory channel versus going to buy large systems that can do 4 to 6 terabytes of memory on that system. You're going to have flash everywhere. You're going to have bootable M.2s that you have in your consumer PCs. They're all coming to the server. Networking. Networking is just insane right now, especially with Intel releasing OmniPath. You're at 100 gigabits per second. And on the machine learning, especially on the training side, you're seeing ingestion needs of 200 plus gigabits per second just to get the data models in to be able to do the training. So we've got that. We've got 10 gigabit LOMs. You've got memory in your processors. The biggest problem with processors right now is all the processor companies just basically gave up trying to keep them low power. And they said, we're all in, man. And I just got out of a meeting. We're seeing TDPs from Intel that are 185. They just said they're coming out with a 200-watt processor. And by the way, it's going up to 320 with some of their bootable accelerators. And by the way, the systems are getting denser and smaller. And oh, by the way, it's my responsibility to go cool it, right? So it is extremely challenging. That's why you see the water cooling system they have in Birmingham is actually going to be, Lenovo's part of our strategy is to be the best vendor out there for water cooling technology. That's where we're putting a lot of our investment. And it's because a lot of the TDPs are going up. The other part of it is standards matter. If you go back to that chart that I was showing you with the curve where x86, a lot of that was because to the left of it was proprietary. So not only do we have to develop systems that have unique technologies, they all have to be open standard, right? Lock-in is bad. And we've been told this from the hyperscale community and also our customers. You've got to be able to leverage tools that you use today. If you change vendors, those tools still have to work, right? So we participate. Some of us are on the boards of these, but we participate in all of these standards. We have representation on all these standard boards. So now, what's our strategy changing? Again, a couple years ago, I said all we have to do is follow Intel roadmap and we're good to go. Now we've got to look at resurgence of specialization, right? We have to be able to deliver a modular platform. So if somebody wants accelerators, I can give you in the same platform that I can do 2-socket E5s. So I got to be able to basically leverage a foundation and make these modular. Everything has to be open. Open everything. So you cannot make something that's proprietary. We have to have open standards. Okay? Co-design is also going to be a part of our strategy, meaning we can't go into a back room with a lot of smart people and develop something on our own and then turn around and say, here it is, how many do you want? That means we have to co-design with communities and co-design with academic institutions and co-design with partners. We have to be very open and say, what is the challenge? Is this good enough? Are we going the wrong direction? And we started this at Lenovo with our customer advisory councils where we bring people in and they tell us how much we suck. They tell us how great we are. We hear everything just because we want to see what we're doing well and improve on things we're not. And then limited budget and higher demands. That one's not changing. That's the same as it is today. Everybody has limited budgets and they want as many cores as you can give them with the fastest network, right? So when able to do that, we got to make means what we got to do is keep our costs under control. It's very easy to over-engineer a server. It's very difficult to only deliver what you need. So these are our design tenets going in. We have these, when we're looking at modular systems, we have to have, these are our 3 design tenets. And we did this for Nextscale. I was on the Nextscale design team, and I have great stories about how we came up with the name Nextscale, if you're interested. It was a religious moment where we all had to sit around and hold hands and see how it made us feel when we heard that name. So you can ask me later, and I'll tell you great stories. But is it scalable? And scalable doesn't mean can you just scale the system by adding more. It means does it scale with cost, and can it scale from an administrator point of view, that it still looks like a single system, whether it be 1 or 1,000 nodes. Is it flexible? Meaning, can I build my server from the ground up, my own? That way I'm only buying what I need rather than buying features but not wanting anything else. And that's the knock on a lot of the OEMs, is that's exactly what we did. And is it very simple? I mean, it's just very basic. I want compute and I want storage, and that's what I get, right? And if you noticed, one of the things that Hyperscale did is they stopped painting servers, and so we did too, because that's $6 for every server. And does it make it faster? No. It just makes it look pretty. So this is where we started stripping out stuff. That took me 3 months to argue at IBM to not paint this. 3 months. They'd go into meetings and they'd say, we got to paint it. And I say, why? Because. Why? Because. That was 3 months. And then finally they just gave up because I was hounding them and not to paint it. So our approach has to be, what do we build? What do we buy, meaning somebody else made in the industry? This is something we never did at IBM. It was always not invented here. Now we look in the industry, especially if you see the NVIDIA box out there with dense GPUs, could we buy that and bring it into the business? Or who do we partner with? And I'm going to move along because I want to get to the cool thing that I want to show you guys where we're at now, is can I build a modular system with these 4 design goals, and I look at a modular enclosure that I can drive anything into it. And I don't have a laser pointer, but the water cooling, the 2-socket Xeon, the Xeon Phi, shared I/O, which I'll explain in a second, is something innovative that we're doing, and ARM all fit into that modular enclosure today. I'm working on FPGAs. I'm looking at the SXM2 from NVIDIA, which is the NVLink-based GPU on a motherboard, and it fits into a single modular enclosure. So this was our idea, and now we're doing it in practice. We can do it for enterprise, and we can do it for specialization. Specialization is where we get the benefit of being able to target workloads while writing what we call the enterprise, where just general 2-socket boxes are basically helping us with our cost, because we're selling things to what we call run rate, just general purpose servers, and then I use that infrastructure and change it over to a GPU, and next thing I know, I don't have to build it from the ground up. It's just a component that I can change out. And that allows us to control not only what we build, but how our costs are leveraged. And then further opportunities. This is something I'm putting, kind of challenging Lenovo to do, which is OCP. Can we release this as an open standard hardware platform that other companies could build towards? And then create an ecosystem, and instead of saying that's Dell servers or Lenovo servers or Cray or Bull or whoever you buy from, everybody builds into this ecosystem, and it's open. So what we've designed here, and this is kind of a sneak preview into our next-gen systems, is a modular server that actually is not just a server, it's front and back. So the front part are these nodes that have the heat sinks on them, and the black where that blue is, that's actually what we call the rear shuttle. This is a 2U 4-node, and it's multiple pieces. The rear shuttle becomes where the PCI goes to. We're taking the PCI off the server and putting it in the back as an option. So if you look at a server that you buy today, you always have a PCI lane. Even if you don't use it, you're paying for it. So what we said is, well, now that you're seeing a lot of SoCs, why don't we just make the PCI optional? And then you can turn it into what you want. So the rear shuttle is power, cooling, and PCI. If I move PCI off the server now, is there something interesting I can do? And the answer is yes, and so we've already done this. I'll be showing it in supercomputing, which is take those 100 gigabit or 200 gigabit, the HDR adapters, ConnectX 4 and beyond. So we're looking at 4, 5, and 6 from Mellanox. And we're partnered with Mellanox. And I put one adapter in and I split it to multiple nodes. So I can isolate the lanes from the adapter and send it to multiple nodes. So what you see is this bandwidth is going nuts, but what most people in HPC care about is the latency. What is the latency node to node? And so we started doing this test where if you look at an FDR to FDR native communication, then you look at an EDR to EDR native communication, latency and bandwidth between the two, could you buy an EDR adapter and go right in between FDR and EDR? And the answer is yes. And so what we'll show at supercomputing is that your network is cheaper and your performance is better than FDR. And it's cheaper than FDR. So it's not native EDR. So we're seeing this in the cloud space where you can buy one adapter, and our next goal is to do this between 4. And if you could do that, all of a sudden you start imagining, can single sockets become relevant in the HPC world again? And the answer is yes. So if I buy one of these 28-core single socket systems, and I buy 2 adapters, I can get 16 sockets in a 2U space, all having identical latency to the socket itself. If I can do what's called shared I/O, so my network costs stay low, and I get to use all these cores a lot more efficiently. Because if you look at the application stack in HPC, they don't scale all that well. So now there's new things that we can look at. In a 2U space, 16 cores, that's pretty impressive. And the other thing we're going to leverage is now this is our Knights Landing. I just got pictures while I was here last night. These servers are now been fabbed. We're looking at them. These are double density bootable accelerators of 220 watts. And we'll go up to 320 watts on these. But this heatsink, there's 2 of them, but these are actually 2 independent servers on a single motherboard. And all of the front space, all that green, is actually the I/O. So we'll route native OmniPath right from it. This is our machine learning platform. So the question says, well, machine learning is NVIDIA. And the answer is, no, it's not. It's actually NVIDIA and Intel, and however you want to accelerate. And so this is one of our launch that we'll do. This came out of a STIC project, which is Systems and Technology Innovation Center. And we're going to productize it. And we're also modifying the rear chassis to make it look very NextScale-like. So now the other modular part of it is I can actually design a system that goes into that tray, and it'll also fit into NextScale. So NextScale going forward will be our water platform. So I can design for one platform for air and then put it into 2 trays, which is also getting us pretty efficient from a design point of view. And our next goal for our future capabilities is to drive 95% energy efficiency or recovery. We're doing some work with LRZ in Munich, and right now we're about 85. We're already working on proof of concepts for like water-cooled power supplies and everything water-cooled in the system, and that'll be our next-gen type stuff. So to summarize, HPC is actually going to continue to be a growth area for Lenovo. So as a company, if you saw my first chart, it had a race car. We are actually what we term the racing arm of Lenovo. That's actually kind of our tagline, and we sold it to the executives that way, and they bought it hook, line, and sinker. So if you ever run into one of our executives, do not tell them I told you that, please. Emerging technologies are very disruptive right now, and they're not only disruptive in the industry, because if you're a user, everybody goes, well, what's the best way, how do I configure my storage? How much memory? What is the best thing to use? And the answer is, we don't know either, because it's so disruptive to us, it's actually changing the way we do hardware design. And I think for the better, though. Open standards are going to remain an important focus for us. We do not want to lock you in. We want to make sure that we adhere to open standards. We think that's an extremely important aspect of what we do. Modular designs are going to be extremely critical with these new technologies, because if you look across the landscape, if I build a server for each one, all of a sudden I cannot recover the cost of what it is to build there, and it's a losing business. And then it's hard for us to partner with people in the industry. And the final is cluster designs moving more towards modular fit for purpose rather than just general purpose. That's where we see the technology trend going. And with that, I think I'm done because I got the little red card up here. And the yank. Yeah, thanks.